Hello. I want to talk about the different forms of the Bernoulli equation because now we're going to expand your horizons and use the Bernoulli equation in other ways. So we have seen the Bernoulli equation in terms of a head, and we mentioned that these head losses were the combination of major losses plus minor losses, right? And the major losses are due to friction, okay? Next Thursday, we'll talk about how to calculate the minor losses, but today we're just going to concentrate on my major losses and then add something else to the Bernoulli equation. So in this form, we are adding now a pump. So a pump adds energy. So if you have the pump between point 1 and point 2, it's adding energy to the system. Now, we saw the losses here, but the losses could also be because there's a turbine. A turbine takes energy away from the water. So you use turbine to generate electricity, for example. So what you do is that flow of water goes through a turbine, and that turbine rotates with the energy of the water, so it's actually taking energy from the water. The pump provides energy to the water. The turbine takes energy away from the water, so it's on this side of the equation because it provides losses. It's like another loss if you have a turbine. So this is the expression that we use whenever we uh, separate the pump. Here you have the losses, and then now you have the turbine. Remember that this is in the units of meters or feet, where you have the head gain due to pump. You have the head loss in the system due to elevation. You have the pressure head, so if you have a pressurized system, and then you have the velocity head. And all of these are in units of meters or feet. So here we have the expression, and you can have them on the left side here or the right side here. Just make sure that if you move them to the left-hand side, that you're subtracting and not adding. So in the head form, we have this expression at the top. If we multiply this expression by the acceleration of gravity, by g, this is what we obtain. Remember that gamma, which is the specific weight, is rho times g. So if you have this expression P1 over rho times g, and you multiply times g, then this cancels and you only have rho. So this cancels, and now you're multiplying times g. So now what we have is an expression of energy per mass of fluid, per unit mass of fluid. Okay, so this is the expression in joules per kilogram. If it was in the US customary system, then it would be pounds put per pounds mass. And then the pressure units, you can express this same thing as pressure units by multiplying the complete expression times the density. So you're left with pressure. I encourage you to do all these derivations of units so that you see exactly how everything is compatible, okay? So then if it's pressure, it's newtons per square meters or pounds per square foot, okay? So mechanical energy of a fluid is very important because one of the things we do is if we have a pump or we have a turbine, we need to determine if we need a pump, how big a pump we need, how much energy that pump should provide. And then if we have a turbine, we need to calculate how much energy you can get from the water. For today, I'm going to assume that the pumps and turbines are like 100% efficient. So this was the expression for mechanical energy. So we have P over rho in joules per kilogram. This is what we saw in the previous email slide here. So this is the mechanical energy in units of joules per kilogram or kilojoules per kilogram. So now we want to talk about power, because whenever we choose a turbine or a pump, what we are using is, if we have a pump, we're adding power to the water, and if we have a turbine, we're getting power from the water. So it's a rate of energy. So the rate of energy would be either joules per second, and joules per second is the same as watts. Okay, so it's a rate. In order to obtain watts, you have to multiply the mechanical energy times a term called the m dot. Okay, the m dot, anything that has a dot, remember, if it has a dot, means that it's per unit of time. So this is energy per time, which is power. So in order to do that, I multiply the mechanical energy times the m dot. And m dot would be kilograms per second, for example. That would be m dot, which is the rate of mass. Or if it's in the US customary, then would be in pounds, and it's pounds mass per second. Okay, so how do we calculate that m dot? And I have it, well, let's calculate it here. So m dot would be the flow rate times the density. Let's do the dimensional analysis. So if I have the SI system and I have cubic meters per second, when I multiply times the density is kilograms per cubic meters. So this cancels and I have kilograms per second. So you need the flow rate and you need the density, okay? So m dot again would be Q times the density, okay? So whenever I multiply this expression of energy per kilogram times the m dot, that's when I obtain power, okay? So here we're multiplying the energy times m dot. I mean, there's different ways of expressing that. So what I have here, this is watts. If it's, and then this would be the watts that the pump can add. This would be the watts that the turbine can get out of the water, and this is the watts of energy that are losses. Okay? So, summarizing the expression for power, then what we have is the m dot, and this here would be power. This is what we call the HD. This was the HT, and this, or equivalent, no? And this would be the equivalent of HL, okay, which would be minor plus major, okay? So this here is kind of deriving the whole expression. So if we have the watts, the power, m dot times delta E, or m dot, now look at this, so it's delta H. So this also, if I have the expression as a head, so the head, I just multiply, let's say that I calculate HD, I just multiply that times m dot times d, okay? And m dot times d, so you have the density times q, which is m dot times g, and then times hd. So another way of seeing this is W, this raw G, let me write G, H, Q also would be H, Q. Now this is a very important expression. So if you had this in terms of head, just the power would be the specific weight times that head times Q. Okay? So this is an example of different situations. So here you have a pump and you have a turbine. So this would not be zero. The turbine is not going to be zero. And of course you have, in this case, pipes. So you need to calculate the losses. So in order to calculate the losses, you calculate the losses at every point. So this would be the frictional losses. Now, whenever we calculate minor losses, anytime you have a bend, we'll calculate that later. But in the end, pump power, it would be this. If we use here the HT, then it would be the turbine power. Okay, important equations. So here, what I have done is summarizing it again. Let's say that you don't want to deal with the energy equation because you feel very comfortable with just expression as a head. That's fine. I just showed you several different forms of Bernoulli. You can just stick to the head, and then when it comes to calculating the power, then you multiply the specific weight times Q times H. Okay? So here is the expression or the derivation of the units. So you have joules per second, and here you have pounds foot per second. But what happens is that we don't generally talk about energy in pounds foot per second, but in horsepower. And 1 horsepower equals 550 pounds foot per second. Okay? Or also, we can go from the US to the SI system. 550 pounds foot per second equals 745.7 watts. This is an example of if you have a turbine. Remember, if you don't have a pump, then it would be zero. If you're talking about the pressure, here is atmospheric pressure, and here is atmospheric pressure. So this is the best way to do it because those are two known pressures, so they cancel. The velocity, if you have, in this case, this is 0.1 and 0.2, so it's at the surface, they would be zero, but the difference in elevation is not. And then you have a turbine, and you will have losses, and in this case the losses are given. So then you just use this expression. Remember that this is the same as saying Q specific weight. This is the equation you need to remember. So since you have a pump, here you have the pump on, since this is the turbine, the pump is zero, you have the turbine on the right-hand side. If it was the opposite thing, that you had a pump, then it would go in the opposite direction, okay? So if you want to move, let's go back. You're moving here the water from point 1 to point 2, then it's a turbine. You're using that energy that is provided by the difference in elevation. If you wanted to go up, then you know you have to overcome 120 meters plus the other losses. Okay? So analogy to a pump, you need to move water from one point to another that's higher elevation. So this would be an exercise that you can do to discuss and provide equations for a pump. Please do it outside of the classroom time so you can practice. That's important that you as a group meet outside of the classroom to build a community. Okay? So just a little hint. If I have to move water from this point to that point, and there's a difference of 25 feet, well, I know that I need to provide at least 25 feet of head, but then I have to add the friction losses to that. So let's say that you calculate the head needed for a pump and you get 23 feet, you know that that's wrong because you need to at least move that head, that water, 25 feet plus overcome the friction losses. Okay? So you take into account the level of the water. In this case, you have 25 feet. So this is what I just said, at least 25 feet plus